Welcome back to another installment of our series on the chemistry of indoor environments. We have been calling this Mastermind Mondays, and that's because I have a mastermind program that if you'd like to get more engaged in all of this and do this kind of work that I do, there's a group of us that meet every month. It's an online self-paced program aside from those monthly meetings. Also, we have a Patreon group, in case you didn't know. We meet twice a month. And on top of that, access to the group coachings, which is where you can see what other people across the country are doing for renovations and additions and new builds, people building their forever homes. So it's a pretty interesting group. Anyway, to this week, what we're going to talk about is some of the things that they found at the NIST facility, which is where the CASA project, which was part of the CIE program, was held. So Michael Link is a great guy. He was in the series Home Diagnosis, season 3. And he spent some time with me. I was a little confused about some things. So if you heard me recently present on this at the Humid Climate Conference, there is a correction that I got some clarification on, and it's pretty interesting. So here we go.
So this morning I wanted to talk about the role of ventilation in maintaining high quality indoor air and 3 lessons that we learned from the net zero house and no diverse bathroom. Okay, so just to represent the diversity of interests that come to this field of indoor air quality, I wanted to simply ask the question, what is high quality indoor air? And so if you ask the indoor air chemist, something that's close to my heart, they might say decreased levels of criteria pollutants, noxious levels of VOCs, you got some good air. If you ask the infectious disease expert, they might say air that's free of airborne pathogens is high quality indoor air. Building designers, they want to increase energy efficiency and recycle traditionally stale indoor air with fresh outdoor air. And then maybe the standard building occupant just doesn't want the place to smell bad.
Okay, so quickly, there are some contradictions within this list. One of them that Michael was pointing out to me is that if you want the ozone level to be low, but you also want the air to be fresh and well diluted, the more you turn up outdoor ventilation, the more ozone comes into the home. And so those two things are at odds with each other. Also, energy efficiency and air quality are also kind of at odds with each other. The very fact of ventilating a home and diluting it with outdoor air is inherently anti-energy efficient. So that's another thing that you kind of have to get around. Also, this infectious disease conversation about the airborne pathogens, we're going to address within this session some of the germicidal warfare that we do in homes. And in general, if you haven't watched all of Home Diagnosis season 3 and seen a lot of the home chem stuff, you do not want to be waging germicidal war in a home because it has all kinds of weird side effects.
Ventilation is a through line for each of these interests, and it's a major control in determining the quality of indoor air. And so I wanted to walk through this example where we took measurements of the air change rate from 5 different locations on this campus to demonstrate the different mechanisms of ventilation that control the air change rate in an indoor space. So plot down at the bottom here, we use the tracer gas dilution method. It's an ASTM standard where we injected SF6 into an indoor space and then we measured the decay rate. And that's what determines the air change rate of the indoor space. And I just want to point out that each of these 5 curves here in that figure are influenced by the mechanism of infiltration. So infiltration is where you have leakage points in building structure, and through a pressure differential, you can get outdoor air coming in, indoor air going out, and then also exchange through different zones of the building. When this mechanism is only at play in a building, for instance, in the manufacturing house on this campus, we measured an air change rate of 0.2 per hour. When we turned on the exhaust fan ventilation above the oven, we could increase the air change rate 0.6 per hour. Mechanical ventilation can be installed in residential buildings as well as commercial buildings more commonly. But for the net zero energy residential test facility on this campus, we have a mechanical ventilation system, and we can achieve air change rates of about 0.2 per hour if we operate that system. In contrast, commercial buildings often achieve higher air change rates. So we measured in the NIST bathroom, the engineering building, an air change rate of 2 per hour.
Okay. So on the left, what you're seeing on that little graph is the SF6 is sulfur hexafluoride, which is a tracer gas that's not supposed to be there. So basically you put this, some people, when I was originally trained, they were like, oh, you use oil of wintergreen, because if you smell wintergreen, it's because you put it there. It's not like wintergreen just naturally was there. So it's the same thing here. They're using this gas called SF6. which is kind of a specialized tracer gas. They inject it, a certain amount of it that they know how much it is, and then they watch to see how quickly that decays. The 0.2 air changes per hour means that there's one complete air change of all the air in the home every 5 hours. And then in the commercial bathroom, they're talking about one complete air change of the volume of air inside of this bathroom twice an hour, once every 30 minutes. Bathrooms in a home would also hopefully do that. I'm generally looking at something more like 3 times per hour, even more in the case of like a small powder room. Even with an ERV exhaust that's only 20 CFM, you could be exhausting like 5 times per hour. So that's basically what the graph on the left is. That sulfur hexafluoride is going to come up again, by the way, in this session. It's a non-reactive gas. It's a very inert gas. So if it's there, you know that it's not going someplace, and it doesn't really like to land on surfaces, supposedly.
And now one final mechanism of ventilation, natural ventilation, you open a door or a window and you're able to introduce outdoor air that way. We opened all the windows in the net zero house and we achieved air change rates of about 15 to 20 per hour. The data is not that great, but all of this to say that rates of air change vary widely between indoor spaces, and they're influenced by a handful of different mechanisms. So ventilation is sort of this catch-all idea to capture all of these mechanisms that influence the air change rate. Okay, so ventilation plays an important role in regulating indoor air quality. And I wanted to just go through 3 different lessons that we learned through our different projects that demonstrate how this works. The first lesson that we learned during CASA was that ventilation brings outdoor NOx pollution indoors and stops VOC oxidation from ozone and hydroxyl radical. I'm showing a time series for NO, NO2, collectively known as NOx, as well as ozone that we measured during CASA, both outside and on the first floor of the residence. And what we observed during this campaign, I guess highlighted, oh yeah, they are showing up. What we observed during this campaign was these uncontrolled NOx plume events. So elevated levels of NO and NO2, we observed outdoors would transfer indoors through the ventilation. And so when you had high levels of NO being transferred into the residence, that NO reacted with the ozone indoors. And so you're not only getting the exchange of indoor or outdoor pollutants indoors, you're also affecting gas phase chemistry that's happening indoors. So under conditions of lower NOx pollution, you might expect ozone to be reacting with VOCs in the gas phase. This can produce hydroxyl radicals. And so you have these 2 oxidants working together to oxidize VOCs in the gas phase, creating a suite of products. However, when we have this higher levels of NOx pollution, you react away the ozone or titrate it away. And thus you sort of shut off this fundamental chemistry that's happening, this ozone and hydroxyl radical reactions. And so, like I mentioned, we care about the outdoor to indoor transport of pollutants, but sometimes the specific transport of NOx indoors can affect gas phase chemistry that's normally occurring indoors.
Okay, let's take a second with this because this is a pretty interesting and complex graphic. So first of all, ozone. Ozone is the grandparent of all of the reactions that are happening inside of homes. Just as a quick review, in case you haven't kept up with all this, chemistry is the creation of new chemicals that weren't there to begin with. This is what we're worried about when we talk about blue lights or ionization or anything more than filtering the air, just taking things out of it. If you add things to the air, you're doing chemistry, you already live in a chemical reactor. So ozone comes in through infiltration from outside, air leakage, and also from ventilation. In this case, we're looking at something like, and this is interesting because I thought when I first started learning about this that like the advice on a really polluted day outside when the ozone is 100 parts per billion outdoors and they say, oh, it's not good air quality outside, stay indoors. I thought that was kind of silly because I know where the air indoors comes from, but it turns out that the house acts as a filter. Basically, ozone is kind of sticky, so it likes to grab onto surfaces. And so when it comes in through gaps and cracks, it'll normally stick to those. So you'll end up with something like a 1-to-5 relationship of ozone indoors to outdoors, meaning that the outdoor ozone level is coming inside, but about 80% of it gets stripped out, and you only have 1 part out of 5 making it all the way inside. By the way, that is from a paper I was advised to like give little annotations. So this is a paper called Indoor Ozone and Its Influencing Factors by Bill Nazarov from 2022. Okay, so the line at the bottom, you can see these big spikes right here. Here, 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 here. They are injecting those. So they're putting ozone intentionally inside. And what that means is that we're actually lowering the amount of NOx, which is nitrogen oxide and nitrogen dioxide, that's inside, the NO and the NO2. These are both not good for people. These are toxic chemicals for humans. So the NO2 is outside, but it photolyzes in the daytime. So when the sun comes out, it starts destroying it and it starts tearing it apart, and then it gets washed away by rain later. NO is generally more prevalent outdoors than NO2. NO2 is mostly created by combustion. And so when you've got combustion, you're going to have more NO than NO2 created. And that goes for your water heater or your gas stove inside. There's a lot of conversation about the gas stoves. By the way, just a quick PSA, gas stoves, electric stoves, induction stoves, they all need ventilation. They all need exhaust hoods over the top of them to go outside. Okay. So NO2 forms when you have ozone and NO, nitrogen oxide. And then it also forms from these things called peroxy radicals. I'm not a chemist, if you didn't know that. So I don't know what that is. But we've got these things being emitted outside. Now, real quick, what we're seeing here is that when the ozone when the NO2 and the NO are spiking, the ozone reaches its low. Then when they go away, the ozone is allowed to come back, essentially. And you kind of keep seeing this relationship. It's almost like looking at, like in a physics perspective, temperature and relative humidity. They also kind of do this with each other. In this case, though, it's because they're reacting with each other. And I think what's really interesting is that if you look at the ozone is not strong enough to fight up against the NO and the NO2. All of these are bad for humans. By the way, ozone is no better. So don't get an ozone generator thinking like, oh, I'm going to get rid of NOx. First of all, it doesn't work, as you can see in this graph, but also they're all bad. So what he's talking about here is that we're getting rid of this normal chemistry that's happening where we're tearing apart VOCs. And by the way, making them into hydroxyl radical, OH, is not that great because ozone tends to be a very picky radical. It'll react with things that have a carbon double bond at the end of them. And I'm not sure that I can know what the picture of that looks like, but I don't know any more about it than you do. Hydroxyl, though, is a much less picky radical. It'll mate with anything that it finds. So that's kind of a more dangerous thing to have happen. So the radicals forming OH is a thing that we also are going to want to avoid. These guys are not making qualitative judgments about whether this is good or bad. They're just noticing the relationships here.
Another lesson we learned was that recovery ventilators are dynamic VOC sorbents. So I'm showing a picture here on the left of the mechanical ventilation system that's installed in the net zero house. And the thing in the middle of that, this blue thing, is the recovery ventilator. It's the core of the mechanical ventilation system that allows it to be an energy efficient process. And there's two types of recovery ventilators. There's a heat recovery ventilator and an energy recovery ventilator. The difference between these two different types of cores is that the energy recovery ventilator allows water vapor to pass through the membrane and you can extract some energy through that process. A question that we asked was, how efficiently do VOCs make it into and out of a residence using this mechanical ventilation system and these two different types of cores? And so in order to answer this question, we simulated a transient pollution event. We smoked barbecue ribs on the back porch of the house, and we sampled the pollution, I guess, right here in the intake of the mechanical ventilation system. We also measured the exhaust of the VOCs from the house right there. And you can see in this plot to the right that we were able to measure VOC decay times being exhausted from the house. And we observed a significant difference between the HRV and the ERV. And what this led us to conceptualize was that the heat recovery ventilator was acting as a dynamic VOC sorbent. And so we observed that outdoor air would come in, it would interact with the core, it would go to the indoors, and then the indoor air would come and interact with the core, undergoing reversible partitioning to the outdoors, resulting in these longer VOC decay times compared to the ERV, which the median VOC decay times were more similar to SF6 decay time. So the ERV was essentially acting as a surfaceless component of the mechanical ventilation system when thinking about VOC sorption. And so what this suggests is that how you construct your mechanical ventilation system can have a significant impact on the outdoor to indoor transport of pollution.
Okay. Now, this is something that I just presented on last week with Grace at the Humid Climate Conference, and I got it wrong. Just in my defense, Michael pointed out that, like, oh, actually, this graphic does make it look like we're saying something different than we actually are meaning. So The way that an ERV, HRV works, it's the same way that it works. It brings outdoor air in, brings indoor air out. Supposedly, the indoor air that we're taking out is already stale. That's why I like to exhaust them from bathrooms. The indoor air or outdoor air coming in is supposedly fresh and not like during a wildfire or some horrific pollution event. So those two things brush against each other on the way through. HRV cores, the thing that they're brushing against each other through, they're not touching each other. The air streams do not touch. They're touching the walls of hallways, basically. They're going by each other, and the walls then transfer energy. In the case of an HRV, it's just heat energy. In the case of an ERV, it's heat and humidity energy. So traditionally, I'm recommending ERVs for this. And what I said the other day, which is wrong, is that it looks like an HRV actually turns around somehow the VOCs that are trying to make their way out of the house and they go back inside. That is not what is happening here. What is happening here is that the HRV is basically taking spikes, and spikes are really what an ERV, HRV is all about. If it's really humid for weeks at a time, an ERV is not going to protect you much more than an HRV will. It will protect you more, but it'll still raise the humidity in your house. The way that these spikes are handled is if it spikes outside for an hour or for 2 hours or a day, the ERV will protect you from that giant spike, and it'll just kind of keep your house running the way that it wants to. By the way, when I say house, I really mean home. This works for condos and TPs and everything. So the ERV is protecting you against those spikes. The HRV is protecting you against spikes only in temperature. And what the HRV is also doing is when there's a spike in pollution that's outdoors that then comes in through the HRV, what the core does is grab a lot of those pollutants. And we're talking about chemicals and particles. So VOCs are volatile organic compounds. They would prefer to be in the air, but they are happy to go onto surfaces too. And in fact, this is a thing that happens indoors all the time. The HRV is acting as a surface that these VOCs, these particles and pollutants in the gas phase that are coming into the house can land on and then just wait. So it's like a battery. And Michael approved of this analogy. It's basically like you're charging a battery. And then for hours after this spike, the HRV is feeding your home the remainder of that big spike. So you get this big pile of food, and instead of just shoving the food through the house and then just grabbing it back out the way that the ERV is doing, which is the transparent kind of surfaceless process. And over here, you can see that the mean of the ERV and the mean of the SF6 were basically the same. It means the stuff is going into the house on a spike, and then it's coming straight out again pretty fast. In the HRV's case, it takes that and then it doles it out to you over a longer period of time. And that gives the chemicals a longer residence time on that surface and a longer time for them to react as well, because of course, ozone is coming in too. And it's then doing chemistry of the chemicals on that surface, and the pollution, just like in the case of smoke, wildfire smoke that we saw in season 3 of Home Diagnosis, the makeup of wildfire smoke as pollution is constantly changing. If you take a sample of wildfire smoke and then 10 minutes later you fly into the same cloud, you take another sample, it's going to be completely different because it's doing chemistry and things are changing drastically. So basically, this is more of we have no idea what's going to happen is the story here. Now, one other thing, I've gotten this question a lot of whether this breakthrough, which is what Michael calls it, of VOCs trying to make their way outside and then turning around and going back inside, whether that happens. And he said that NIST, which is again the National Institute for Standards and Technology, has no indication that this is happening at all in ERVs, and obviously not in HRVs either. The HRV thing was confusing because they're made of plastic or metal, which is a lot harder for things to turn around in. So this breakthrough is not happening in ERVs or HRVs as far as we know so far.
And finally, one of the last lessons we've learned most recently is that increased ventilation can reduce aerosol byproducts from the operation of UV disinfection technologies in an odoriferous bathroom, and specifically the odoriferous men's bathroom in the engineering building on NIST campus. Earlier this year, we worked on developing a standard test method for the chemical assessment of air cleaning technologies. And we came across germicidal ultraviolet light with a peak emission at 222 nanometers. And in some work we published earlier this year, when we deployed these lamps in our chamber, we saw substantial amounts of ozone being produced, as indicated by the black line right here. And so that's really important because if you're introducing a source of ozone to the indoor environment, you can do gas phase reactions, you can do surface reactions, and can produce a suite of byproducts that we might be concerned about.
Okay, now on the left, you're seeing all of these reactions. What you're seeing here is 222 nanometers. Okay, so there's two main kinds of ozone lights, excuse me, UV lights that they've got out. One of them is called hot upper room germicidal UV. And this is like when you walk into a restaurant after any time from COVID after, there are these like blue lights that are kind of sconces high on the wall. Those are emitting 254 nanometers. That light, the reason they use it in the upper part of the room is because it is going to give you cancer if you interact with it. And it is creating hydroxyl radicals. That is what 254 nanometers specifically does. It's trying to get at the most reactive species of chemical that we can make up there, even more reactive again than ozone. 222 nanometers is something that a lot of people have insisted does not create ozone. And this is something that has been recently disproven. So the manufacturers of these UV lights are now admitting that it does create a little bit of ozone. And how much is a little bit? It kind of depends on how dirty the light is, how old it is, how well maintained it is, all this stuff. Also, what kind of reactions it's doing in your air, because like what's in your air in a home, totally unpredictable. No one knows. It's based on your face lotion and what you cooked last night, what you cleaned with this morning, etc. Okay, so essentially every UV light is basically an ozone creator, and so we can kind of assume that. Now, there is a standard on this that we're going to get to. The reason that people used these during COVID was because restaurants, like public places, were a little bit more worried than simple homeowners because they didn't want to get sued for killing a bunch of people. And so ASHRAE has this standard called 241. ASHRAE has another standard called 62.2, which I talk about a lot on this channel already. That's about residential ventilation. This is about control of infectious aerosols. And so it prescribes either ventilation, or if you can't do ventilation because your HVAC system isn't good enough, then you can do this disinfecting technology. Now, we're going to get into standards in a little bit more in a bit. But the thing to understand here is that these do create ozone, and basically it created more ozone the more it went. These little purple dots down here, by the way, are for the people who are like, well, maybe the ozone was there anyway. This is what the ozone level was when they taped over the UV light. And so it basically went completely away. It was all this UV light that was doing it.
We wanted to take some of the results that we observed in our chamber and ask what would happen in a typical installation in a real environment. And so we commandeered the men's bathroom on the first floor of the engineering building, and we set up these lamps. And one of the peculiarities of this set of experiments was on the first weekend, the mechanical ventilation system in the bathroom was broken. And we learned that we took a barometer and we're like, oh, it doesn't work. No wonder it's so terrible in here. And so we had a lower air change rate in the bathroom. It was about 0.85 to 1 per hour. On the second weekend, we got facilities to fix the mechanical, the motor. So we increased the ventilation to 2 per hour.
Okay, quickly, odoriferous means stinky, but it's very vague because they didn't want to be too specific. Chemists like to be very specific about things. So when it comes to like bathrooms, I was like, it looks like this bathroom is so taken over with equipment that no one was actually using it. I was like, I would like to see it when somebody's actually doing number 2 in there. And he was like, we did. And then he didn't say anything else. And so like, again, it's gross to talk about, but like, yeah, it sounds like they did use this bathroom or encouraged it to be used. Now, just to review, it was broken at the government facility where the nerdiest building scientists work. So if this bathroom ventilation was broken, your home ventilation could be broken right now, and you would absolutely not know. These guys would be the ones who would know, and they didn't know. So again, testing is everything. Just test it.
There's a lot going on here, but I'll try and walk through as quickly as I can. On the left, I'm comparing low ventilation to high ventilation ozone production from the germicidal ultraviolet lamps. The black line is showing the background. So what we would expect in the absence of the UV technologies, you turn on the UV technologies and the blue is showing the ozone that was generated. The top four panels over here, top four panels over here are showing particle number concentrations, and the bottom four panels over here are showing particle volume concentrations. On the first weekend, what we saw was substantial amounts of particle numbers being generated right here whenever we operated the UV lamps. And one of the mechanisms that was going on was nucleation. So we were oxidizing things in the gas phase. They were forming condensable vapors. These condensable vapors were coming together to form particles. We were getting nucleation. Additionally, we were observing evidence of condensation coagulation. So particles were growing to larger sizes and resulting in measurable particle volume differentiated from the background. So basically, chemistry plus low ventilation giving small particles can make big particles. On the second weekend, we still saw the formation of particle numbers. And so we still saw some nucleation, but these particles were staying at these smaller sizes. They weren't really growing out of the 30 to 40 nanometer count median diameter range. And so we observed minimal volume growth, and we weren't able to observe any particle volume that was easily differentiated from the background.
Okay, now I'm just going to review what he just said because, like, you're not a professional chemist. This might not make sense to you. This is with the lower ventilation rate and the higher ventilation rate. First weekend when it was broken, second weekend, right? Basically double. So it was 5, maybe in the hallway in both cases. As soon as they turned on this germicidal light in the bathroom, it elevated. And you could see that with this blue line here. Okay, so there's that. It's the same in both cases, roughly the same, about, at 5 extra parts per billion of ozone. What that ozone was doing then was making particles. And so the number of particles went way up. You can see here in the lower ventilation. But then look at this ramp down. What is happening there is that the diameter of these particles was very, very small. 500 nanometers is the biggest thing on this graph. That's right here. That's half a micron. 2.5, PM 2.5 is 2.5 microns. So this stuff is at biggest 1/5 the size. And in fact, you're looking at on the chart here, it says about 100 was the biggest diameter that we had in nanometers. That's about 1/25 the size of a PM 2.5. And by the way, a human hair is like 80 or 100 microns. So this is really, really small. This is like 1/200th the size of a human hair. Really, very small. What happens at that point is that over time, you can see hours going by here. There's this big plume of the number of particles. And then what happens is over time, the volume of them goes up. And that is because they're growing. So they're like joining together and then they're condensing. They're getting big enough that they can form condensable surfaces, and other molecules are condensing onto them. And then you end up with these much bigger things, which end up being what we call PM 2.5, which is a health concern. Over here with the higher ventilation, you see that it does that, but it doesn't really get the time to form this solid block of what's going on here. You can see that this scale goes up to 4. This scale only goes up to 2. And likewise here, this one goes from 0 up to 15 or 20. This one goes up to only 4 or 5. So the rates, the amount that we're creating in these two is very different. Don't be fooled by the fact that they look the same size. They're actually like very different sizes. They just adjusted the parameters.
So chemistry plus higher ventilation gave us small particles. And this is interesting to us because when you have larger particles, we think about particle mass as a metric for negative health outcomes. Perhaps excess mortality as a function of PM 2.5. Under the conditions of higher ventilation, we're generating small particles. Small particles can penetrate deep into the lungs and represent a unique exposure route. So this is a case study on how ventilation controls the production of 2 different aerosol byproducts. And also what it demonstrates is that because of changing the ventilation rate, we saw that the timescales of which the chemistry was contributing to these aerosol byproducts was comparable to the ventilation timescale. So I'll leave it there. I just want to say 2 broad statements. One is that continued fundamental research to support the development of indoor air quality standards, I think, is an important North Star potentially in the community. In the outdoor community, we have the NAAQS, National Ambient Air Quality Standards. And without a set of standards to refer to as we go forward in our studies and research, it'll be really difficult to understand how to construct the indoor environment to increase high quality indoor air.
Okay, now these standards that he's talking about, mostly what he's talking about is ASHRAE 62.1, which is a commercial ventilation standard. ASHRAE 62.2 for homes is actually doesn't really take any monitoring into account at all. It's just a prescriptive, like, here, do this, and it should be fine. In 62.1, I believe that they monitor CO2. They're using carbon dioxide control as a metric. And what his problem here is that none of these standards, including ASHRAE 62.1, ASHRAE 62.2, ASHRAE 241, that infectious aerosol control standard, none of them, and including, by the way, HVI, which is the Home Ventilating Institute, they certify things like bath fans and ERVs. None of them are considering chemistry interactions. And so when they say, oh, you should do this, they're not thinking about what's going to happen in terms of chemical reactions. And that is dangerous. And by the way, you're already exposed to the effects of this because materials certification, like, for example, Green Guard, or if you look at stuff where that, like, USGBC's LEED is going to accept into their program, or, flooring certification, things like that. None of them, some of them are very fraught with double intentions from the manufacturers are very involved in those. Let me just say that. But none of them is considering chemistry of those materials either. And we talked about that with the urea formaldehyde issue in the 1970s and 80s. That was, again, in Home Diagnosis Season 3. If you haven't seen Home Diagnosis Season 3, highly recommend it. It's really good background for this because you'll meet a lot of these researchers who you're seeing in this series, and you'll get to hear a lot more about what they have to say in lay people terms, because, of course, again, these are PhDs talking to other PhDs. So just consider that all of that stuff is important when you're thinking about the materials that you're choosing, or when you're thinking about how to ventilate. None of it is like standardized, or there's no guidelines around this chemistry stuff. That is what this series is doing on this YouTube channel right now. So you guys are literally watching history get made. It's really fun to be a part of.
And when we can get a sense on what indoor air quality standards might look like, we can make some updates to ventilation standards that reflect new understandings of indoor air chemistry. So I just want to acknowledge and thank everybody here, CASA people, NIST people, and I'd like to thank you for your attention.